think we're all here and we're ready to begin. Let me first, before I introduce Alex and let him begin his defense, I want to cover a few admin things. I want to introduce myself. My name is Gene Paulo, Systems Engineering Department. I'm the chairman of Alex's PhD committee. The rest of the committee is here. I'll quickly introduce them. Cliff Whitcomb, the chair of the System Engineering Department. Arnie Buss from Moose Institute. Tom Lucas from the OR department, and Andy Hernandez from the Systems Engineering Department. I also want to introduce Andrea Cameron. She is our academic council representative. I want to thank you very much for being with us today. A couple other points. Many of you, maybe most of you, have been through a dissertation defense and the procedures that happen. So just to let you know, Alex has submitted his, what I think, or most of us think, is approaching or is his final draft for his dissertation, and the committee has been reviewing it, and so now he is ready to present his research to us and to all of you who have been able to come today. My perspective is that we've set aside 2 hours, but I think we want to shoot, I'm going to try to shoot for about 90 minutes total. We believe that his presentation will take 45 to 50 minutes. Then we'll open it up for questions. The first round of questions will be for the committee members to ask questions as they would like. Then we'll open it up to the rest of the audience. And then we'll stop at an appropriate time. We'll ask everyone to please step out while the committee members and the academic council rep meet and make our final decision based on our discussion. So that's how it's going to go. And I will now go ahead and introduce Alex. Alex MacCalman's, Lieutenant Colonel in the United States Army, graduated from the Military Academy in 1995. He got his master's in operations research from the Naval Postgraduate School in 2007. He is an officer in the Special Forces. He also has a functional area that he works in operations research, systems analysis. We label that as 49 branch in the Army. His follow-on assignment when he leaves here and finishes is to go to the Military Academy again, and he's going to be on the faculty in the Systems Engineering Department. His research as a MOVE student, and you can probably see this here in the presentation, you'll see who the committee members are. This research as a MOVE student involves operations research and the Systems Engineering Department. So it's really interdisciplinary and very significant, I think, and of interest to all of us. And one final thing, next week, Alex is deploying to Afghanistan to conduct research for the Defense Analysis Department. So with that, I will turn it over to you, Alex, and the floor is yours.
Thanks. Good morning. Thanks for coming. My purpose today is to talk about an original contribution to knowledge that I was able to accomplish in the form of an experimental design. And this experimental design can be labeled with this title called Flexible Space Filling Designs for Complex System Simulations. And the agenda I'm going to follow today, I'm going to first talk about a background of experimental design, specifically as are used in simulation studies. And then we'll go into with specifying my research goals, and then I'll give you a visual depiction of where my research fits into the literature, the body of literature. Then we'll transition and talk about how we created these new designs by using a genetic algorithm. And then we'll transition to a topic where we go through and convey the utility of these designs, give you the so what, or why they're significant and why they are a contribution. And then I'll conclude with what the contributions are. So first off, I want to key in on the importance of computer simulations. When we model things or systems, whether they exist in reality or we're trying to conceive them from nothing, we're trying to get a better understanding of these complex systems by leveraging computer simulations that account for all the complexities that may occur. Now, these simulations underpin a lot of important DoD decisions, and they're involved in all areas of science. They're often used when physical experiments can't be performed because they're too costly, and when systems don't exist. Now, simulations typically have a whole host of inputs that go into the models. They could be in the hundreds or even thousands of input parameters that we're interested in investigating to see which ones have an important impact on a number of outputs. And more often than not, there are several outputs that could be coming out of these simulation models that we're concerned with. And we want to understand the significance of each one of the factors that are going into these models, but not only the important factors, but to understand the nature of those factors' behaviors. Whatever input goes into the simulation, how do they affect the outputs that we're concerned with across a multitude of outputs that come out? Now, the best way to understand the input and output relationship for a simulation model is to leverage the field of statistical design of experiments, where we create a simulation model that models the real world as an abstraction of reality, and we leverage these design matrices, experimental designs, where in this matrix the columns represent the input factors that are going into the model, and the rows are the experiments that specify the experimental settings for each one of the inputs. So with these designs, the contribution I'm making is a new type of design of experiment or design matrix that we can use to analyze models. When we perform these experiments, we end up with an output vector of multiple vectors, if there's multiple outputs, that we're trying to understand how this output, which is often referred to as a response because it responds to the inputs of the simulation, how does this response, the landscape of this response, behave in some way? And it's often called a response surface that we're interested in trying to model. Now, the best way to quantify the relationship between the inputs, these inputs and outputs, is to leverage use ordinary least squares. Is a very common fitting technique to create a polynomial parametric equation or a function called a metamodel. An example of a metamodel is right down here, and this happens to be called something called a second order metamodel. This is a metamodel because it acts as a model of a simulation, which is a model of the real world. That's why it's known as a metamodel. And in essence, it's a surrogate to this simulation. And what it does is parametric equation expresses the important factors by these linear terms, and the important factors typically have a slope that has other than 0 that express the rates of change of how it impacts the output that we're investigating. The other higher order terms capture some of the nonlinearities, some of the interesting behaviors which lead into the nature of how these factors are performing. The quadratic effects show the nonlinear behavior that may indicate some knees in the curve or diminishing or increasing rates of return. And these two-way interaction terms also give an idea of what the synergistic effects there could be existing between two factors. Now, in order to create this metamodel here for a second order model, we not only have to use the input factors for the linear terms, but we have to expand this matrix out to include all the quadratic terms and the two-way interaction terms as their own separate columns. And that would be defined as something called as a regression matrix. A regression matrix is something that we use to fit with ordinary least squares to come up with these parametric metamodels. Now, this metamodel, called the second order model, happens to be the most common metamodel used to analyze complex simulation. And the reason why that is because it has a wide variety of response surface shapes, whether it's high points or low points or valleys or saddles or synergistic effects between two variables. And it is able to understand these complex behaviors that could result of these outputs. But they do have limitations. Second order models, typically in one dimension for a particular factor, only have one inflection point, meaning it may go down to a low point and then back up, and that's really about all we can capture. There may be times in your analysis that you want to be able to capture a couple inflection points or maybe 3 inflection points, which would require a higher order model. For example, a third order model may have 2 inflection points where it may go down in one area of the experimental region, come back up, and then down again in some other area. So we want to have the flexibility to not only fit the most common metamodel that's out there, but also the flexibility to capture the higher order terms if necessary. This slide talks about the importance of orthogonality. And the key is this top bullet. In order for us to understand the true nature of a simulation, we want to ensure that we have accurate estimates of the coefficients of this metamodel down here. These coefficients are expressed by these beta coefficients, these beta terms. And our objective is to try to get them as accurate as possible. Now, it turns out when we use a design matrix, if the columns are correlated with each other, if there's high correlations between them, then there could be significant impacts in the analysis and the results in our ability to get accurate estimates. And I've got 3 of them here that I'm going to list. The first one is that if we perform ordinary least squares and fit these metamodels, and it turns out that a particular input factor is statistically significant, but it happens to be correlated with some other column, then we can't tell for sure whether it's the one that's statistically significant or it's the factor that it's correlated with. So in essence, it confounds the analysis. We don't know which factor is impacting the output, and it screws up what we're trying to accomplish. Now, the second point is this notion of model bias, and oftentimes when we fit these high-dimensional complex metamodels, we don't often include all the terms that could actually be in the true response surface. Now, we never know what the true response surface is. That's why we're performing these experiments. Otherwise, we wouldn't perform these experiments. But when we exclude some of the terms that may be in the true model, that could result in a completely inaccurate estimate in the actual coefficient itself. In some cases, if the true model is a positive slope, meaning that the rate of change increases as you increase from the low to high setting, it may come out in the metamodel a complete different sign, which it could be a negative slope, and that could cause a misinterpretation of what the impact of a variable will do on the output response. And lastly, it inflates the variance. These variances we perform multiple replications of the simulation because oftentimes simulations have a stochastic nature about them, so we do multiple replications to understand the variance of the output. But when we fit ordinary least squares, we're also concerned about the confidence interval that results from these beta coefficients. And ensuring that those confidence intervals are as tight as possible will increase the precision of these estimates and ensure that they're as accurate as possible. So to conclude, we're trying to minimize the correlation between each of these columns so that we can ensure that the most common metamodel used to analyze complex system is going to give us the results that we desire. Now, another important characteristics for experimental design is this notion of space filling. And what space filling means is that within an experimental region, in this example you see two factors of interest, one on the x-axis and one on the y-axis. And inside are the settings for each of these two factors, the combinations of factors. And when it's a space filling design, it fills the interior of the experimental region such that you've got multiple lenses to try to look and try to identify interesting behavior that's going on inside the experimental region. Whereas over here on the left, there's these things called traditional second order designs that are specifically suited to try to capture the second order model. And in order to do that, they have to sample at the corners, the endpoints, and center in order to come up with those nonlinear curvatures. But the limitations in these designs is that they only can fit second order regression matrices, and they cannot look inside the interior of the space to find interesting behavior. And oftentimes in complex simulations, we have these things called thresholds, which I have an example of here in this upper left corner, where you have a second order response surface, but you have some interesting behavior or a region of the response surface that's vastly different than everywhere else in the response surface. And as a result, you want to be able to capture where those interesting localized effects are within the response by filling the space and identifying it. So these two-dimensional projections of this response surface shows this blip in this interesting behavior here, and a space filling design can potentially capture that, whereas the traditional design that only looks at the corners cannot. Now, it turns out that a Latin hypercube is one of the most common experimental designs used to analyze complex simulations. And really, it's because of their exploratory ability by filling the space. By the nature of its construction, it fills the space very well. They're constructed by randomly permuting the numbers 1 through n being the number of rows in the design matrix, in a random order. So, for example, up here, there's a two-factor design with 6 experiments or 6 rows with the numbers 1 through 6 randomly permuted to get the column. Now, despite them having an excellent exploratory ability to come up with a good understanding of what's going on inside the response surface, they have inherent correlations that could result. And this is just an example of this 2 columns, and this is a two-dimensional projection of factor 1 and 2, and you can see that they're correlated with each other. Now, when you're analyzing these simulations, it may turn out that when you perform these experiments and you have a good response or an output response down here in the lower right and a bad response up here in the upper left, it's hard to tell which factor is impacting the results, and you can't tell. They're confounded. So again, minimizing the correlation is something that we're concerned with. And up to this point, there's been a lot of research done in the operations research department to come up with a type of design called a nearly orthogonal Latin hypercube. And these are Latin hypercubes that minimize the correlation between all linear main effects so that the maximum absolute pairwise correlation is below 5%. Now keep in mind, they only do this for the linear terms only. They do not do this for the second and the second order terms. Now this leads us to our research goals. So I'm going to identify what the current gaps are and our research goals to fill these gaps. First off, the traditional second order designs that capture these second order nonlinear models, they are inflexible in that they are not able to create a third order or fourth order or whatever higher order regression matrix to be able to capture or to fit these higher order terms. And the reason why they can't is primarily because they only sample at the corners and midpoint. And as a result, when they expand out to those third and fourth order terms, there becomes a linear dependent column within that matrix, which doesn't allow you to invert the matrix, which is a necessary operator within linear algebra to perform ordinary least squares. So as a result, they're limited in their ability to expand and look at higher order models. And again, because they only look at the corners and center, they don't fill the space properly to find out interesting behavior. Now, the gap within the space filling design domain is that there are currently right now no space filling designs that can minimize the correlation between all second order terms. And that's certainly something that we're trying to address. Because at this point, there's a trade-off between our ability to minimize correlations for a second order model up at the top and our ability to fill the space by simultaneously minimizing the correlation. So we want to address this trade-off by creating new designs that do both. In the past, experimenters had to make a choice. They had to choose for these designs or the space filling designs, and there was trade-offs among them. So by creating a new design that can address both these issues is what we're trying to get after in this research. So these designs will minimize the correlation for a full second order model, simultaneously fill in the interior of the space, and in addition, have the ability to fit multiple meta-model response surfaces, not just second order or first order, but also, if need be, third or higher if we so desire. Because oftentimes our simulation outputs have multiple outputs, and each one of them have their own unique response surface that we're concerned with. And we can do this in a single experiment. And lastly, we want to make these designs freely available by creating a custom design creator that could be used by the wider community to not only have the experimental designs that include continuous factors, but also discrete and categorical factors as well. Now, in my earlier I talked about how I was going to show a visual depiction of where this research fits into the body of knowledge. And what I'm doing here is I'm specifying two domains, the space filling domain up here and the second order domain down here. In terms of the space filling domain, this came about when the computers became popular because all these space filling designs are computer generated designs. And back in the early 80s, they started out with the Latin hypercube sampling. They've evolved to try to improve the correlation among the columns. And recent advances here lately, we've done a lot of success here at the Naval Postgraduate School to minimize the correlations for the linear terms only. Down here in the second order domain, this has started out back in the 1920s with the inventions of the experimental domain science. And it started out with the agricultural research, and it progressed over in time by doing some industrial experiments in the 1950s to try to capture these nonlinear terms that can exist. And this certainly advanced up to the point now when the Sanchez's here at the Naval Postgraduate School were making these designs extremely efficient. But again, although this is a tremendous contribution by being able to capture these higher order effects, they weren't able to fill the space like the space filling designs could. So that's where our research comes into this junction right here, where we're combining both domains and creating new designs that both fill the space and minimize the second order correlations. And in addition, we pushed it even further to the right by including or advancing the type of designs to ensure that we can have second order discrete factors as well. And we'll get into that later, what those are. Okay, now we're going to transition into our next portion of the brief, and it's going to talk about how we create these designs. We created these designs using a genetic algorithm. In the past, the researchers up to this point have traditionally used math programming to try to come up with a model, a linear programming model to minimize the correlation between all linear terms. And because our domain has quadratic and two-way interactions, they've got higher order or nonlinear terms. Now, it certainly is a possibility to use nonlinear programming to try to solve this problem, but even nonlinear programming may not guarantee an optimal solution in some cases. So in terms of our ability to try to address this problem, we chose to use the field of genetic algorithms because they do provide a robust search mechanisms, and although they don't provide an optimal solution, they're a heuristic that provide very good solutions, And because we're trying to find nearly orthogonal designs, we thought that a genetic algorithm that can be written in a freely available Java code and does not rely on expensive optimization software, it would make it more widely available to the community and be able to address the need by finding these designs by using genetic algorithms. Now, the basis of genetic algorithms essentially tries to find solutions by creating an initial population of solutions and evolving them over time with multiple generations, randomly picking from old populations of solutions, solutions that are performing well in some way by determining a fitness function, and evolving them over time so that eventually these generations will improve and end up into a localized solution and hopefully end up with a better solution in the end. Now, they traditionally do this with something called an operator, and these operators are unique to the problem. In our genetic algorithm, we have two types of operators. Because in the algorithm, when it starts out with one randomly generated column, and then it successively or iteratively adds an additional column to it, so that when that column is added to the particular design, it happens to minimize all the correlations for the second order terms. So we do it one column at a time. And as we do this, we use the swap operator to randomly swap different row positions in the column a random amount of times. Until the end, we perform these swap operators on these columns until we get the required number of columns that we specify in the initial settings. And when we have the design that we want, then we move into this jiggle phase, and we perform the jiggle operator, which in this case, what we're doing is we're taking out each of the columns that we've created, and we are going to add a small perturbation, a small value to a particular design point, and take that same value and add it to one value and subtract it the same value to another value within random positions of this column. And in the end, the hope is to find a design matrix that minimizes all correlations for the second order model. Now, every genetic algorithm has a fitness function that we're concerned with, and that's one of the benefits of using genetic algorithms is that we're not limited to the form of that fitness function or whatever it could be. In the past, the fitness functions, or what they tried to do was only minimize the correlations among linear terms. What we're doing is we're not only doing it for the linear terms, but we're also minimizing the correlation among the quadratics and the two-way interactions amongst all these pairs. The correlation equation is expressed right here. So in order to get our fitness function, which happens to be the maximum absolute pairwise correlation among all second order terms in this regression matrix, depending on how many factors there are, we have to go through and calculate every pair and find the maximum absolute. We don't care about whether it's negative or positive. We just want to know if it's high. So from here on out, I will specify this term called row map to be the maximum absolute pairwise correlation for all second order terms, or whatever terms that are in the regression matrix. This becomes our fitness function that we're using in our algorithm. Now, to give an idea of the complexity of the problem, what I'm showing you here are the number of pairwise comparisons or calculations that we have to perform in order to get the row map for a second order model. Now, for a first order model where it only includes the linear terms only, you can see the blue line here. It doesn't require many pairwise correlation checks or calculations. But for a second order model that includes the interaction term, it increases tremendously. Just to give you an example, for a design matrix that has 15 columns, if we're only concerned about the linear terms only, then we have to perform 105 correlation checks, pairwise correlations. Whereas if there was a full second order model that includes quadratics and two-way interactions, we would have to perform 9,045 correlation comparisons in order to get the row map that we're looking for. So because this algorithm is generating millions of columns at a time as going through the evolutionary algorithm, performing that 9,045 times, millions of times, is a lot of computation, and it ends up slowing down the algorithm. So in essence, it bounds the amount of columns that we're able to capture because of the complexities and the amount of two-way interactions that explode as the number of columns increase. Now, again, I should point out the number of columns also is the number of factors that go into your study. Okay, now I'm going to give you just a strategic overview of what this genetic algorithm does. Not the details, but just kind of give you a sense for how we're creating these designs. And the first thing we do is we start out by generating a randomly permuted column that has the number of rows specified by the user. We then move into an exploration phase where we have multiple sets of initial populations of candidate columns that we're going to hopefully add to this to minimize the row map. For each trial, the exploration trial, we generate a set number of populations of candidate columns, and then we create additional generations by selecting with a probability that's biased towards a low row map among the columns, different columns over time and performing the swap operator as I described earlier. After multiple generations, the number of generations is specified by the user. You're going to get the best column it was able to produce, and then it's going to move on to a new population and try again. The algorithm is very contingent on the initial conditions, meaning the initial column it started out with, and also the initial population of candidate columns that it's trying to add to. So the idea of having an exploration phase to start out with multiple initial conditions allow us an opportunity to hopefully find a minimal correlation for the row map. Once we perform the exploration trials, we'll then move into the exploitation phase by taking the population that contained the best column and exploiting that population with additional generations until it improves it as best it can. At the conclusion of the exploitation generations, we'll then take the best column from that population and add it to the design. When we started out with one column, we now have two columns. And just depending on the number of columns that we specified in the initial settings, it'll continue the steps 1 through 4 until you have the desired design with the number of columns specified by the user. For continuous factors, we then move into the jiggle phase by performing this jiggle operations as I described earlier, where we take each column in this design, pull it out, create additional candidates from this column that we pulled out by performing the jiggle operator on this column multiple times, and then continue the generations until it improves it as best it can. And at the end, if it happens to improve the overall row map for the design, it'll take out the old one and put this new one in. If it doesn't improve it, it'll just throw out the one and keep the original one in. It'll do this for each one of the columns, and then at the end, it'll pass through and perform this operation again across all columns for a set number of times. So at the conclusion of the algorithm, you're going to have an experimental design with the best row map that it was able to find. Now, all genetic algorithms have a host of input parameters that oftentimes are difficult to understand what are the appropriate input settings for these algorithms. So it happens that our algorithm was very stochastic in nature. So I've got just a little snapshot of an output where the y-axis is the row map that resulted in the design that it created, and on the x-axis are just a host of design points that are instantiations of the algorithm. And really the point here is, despite it being very stochastic, we still want to try to tease out and understand what are the appropriate settings for the input that improve the search space. So to do that, we performed an experimental design on an algorithm that creates experimental designs. So to do that, we had a number of questions that we wanted to study. The first one, because the swap parameters and the jiggle parameters operate completely independent of each other based on where they are in their phases, we set up experiments where we're trying to find out and understand the behavior of the algorithm by seeing which the swap parameters mattered most and what their appropriate settings should be, and also a separate experiment for the jiggle parameters. And lastly, we did a third experiment to try to see and find out how many generations were necessary before the solution converged to a local solution, and it really didn't benefit us to continue with the generations. Although we may get lucky if we continue to perform those generations, but in general, was there an appropriate setting for the number of generations performed during the algorithm before we should just give up and move on? Additionally, in the end, we ended up coming up with an appropriate input parameter settings for the algorithm so that the user can just use them and put them under the hood and have them available to. But in addition to trying to find the appropriate settings, we wanted to provide guidance on how the algorithm performed and also how long the algorithm takes for different values of rows and columns, or N and K, because ultimately that's the input that we're trying to get. We enter the number of columns we want, the number of rows we want to execute the algorithm, and we want to see how it performs and see how long it takes. So in terms of performance, all these are for continuous factors, and we have these 6 charts here. Each one of them is for a design matrix that has 7 columns or factors, 8 up to 12 factors. On the x-axis is the number of rows in the design matrix, or levels is another word for that. On the y-axis is the row map that resulted from the design that was created by the algorithm. Now we performed the algorithm multiple times with multiple replications so that we can capture a box plot which shows the variability of output in terms of the row map that resulted from the algorithm run. And what we're interested in is what number of rows are necessary to get below the threshold of 0.05, which is something that defines what a nearly orthogonal Latin hypercube is. And despite all these experiments, we found the appropriate input setting, or the appropriate number of rows that are necessary to get below 0.05. But what's interesting that you can see here is that there certainly is a lot of experimental savings that you can do. Every row is an experiment. So the least amount of rows, the more efficient the design is, the less computation time is required when you're performing your experiments. So you may want to give up a little bit of correlation and settle for a design that has a 6% correlation instead of 5. And as a result, you may save yourself from doing 200 experiments. So it really is going to be up to the user whether they're going to be able, depending on their experimental conditions and how much resources they have to perform these experiments, whether they want a design that is as efficient as possible and accepting a correlation that's a little bit above 0.05. Now, in terms of timing, what this slide shows is on the y or the x-axis is the number of rows, again, the number of levels. The y-axis is the number of hours the algorithm took to perform or execute. We performed these particular runs on the Hamming computer here at the Naval Postgraduate School. The Hamming computer is a high-performance computer cluster. It happens to have 2,000 CPU nodes that we can use somewhat simultaneously, depending on what's in the queue. And by leveraging our high-performance computing capabilities, we're able to perform a lot of algorithm runtimes, not only get an understanding and provide guidance in terms of timing and performance, but really to execute all those experimental designs that we did earlier, and to continue to do experiments to find designs that have the lowest row map possible. So in the end, we probably have about 25 years of computation time that we use not only in the Hamming computer here at MPS, but also some of the high-performance computer resources that are available for DoD outside of MPS. Now, in terms of the performance of how long the algorithm takes, you can see it here. If there's 7 or less columns in the design, it doesn't take much time at all. But if you give above 10 factors, you may have to wait a day. And the more the factors increase, the more variability the time is. So it's something to consider. Now, with all this said, we've cataloged designs up to 12 factors so that you don't have to do this anymore, so that you can become consumers of these experimental designs and not have to wait 3 days or whatever amount of days it takes to execute this algorithm. Okay, so now's the so what. We talked about the background of what experimental design is. We talked about how we got them. The next thing we're going to do is to give you the so what. And we're going to do this in 3 ways. We're going to first do some comparisons of the state of the art. And then we're going to do some empirical experiments on the performance of the designs. And lastly, we're going to talk about an application that we use these designs for with a model-based system engineering application. So first are the comparisons. What we're showing here, well, first of all, we established the baseline. Excuse me. We established the baseline where we took one design that had 4 columns and 25 design points. And we used that to compare our design with as many of the state-of-the-art designs that are typically used in all the classical experimental design textbooks that you see here in the outer perimeter. Our design is in the middle. You've got a mix of space-filling designs and second-order designs that we certainly don't need to get into the weeds of what these are, but just know that there are classical designs that are commonly used within the field of statistical design of experiments. And what we're showing you here are correlation plots. The correlation plots, because there's 4 factors, that means there's 14 terms in the second-order model when you include the quadratics and two-way interactions. And inside these colors, the color black is a correlation of 1. The color white is a correlation of 0. Everything in between is the shade of gray. So what we're getting out of this, certainly, is that the second-order nearly orthogonal Latin hypercube has the most white space, or minimizes the correlation with a row map of 0.032 for this particular design, whereas all the other leading state-of-the-art designs have some problems with their second-order correlations. Now this is a chart, the same designs that we showed you earlier, but this time we're showing the two-dimensional projections to understand what the space-filling characteristics are for each of these designs. And the way we're doing this is we're showing these projections because there's 4 factors and they're two-way projections. 4 choose 2 means that there's 6 projections that we're looking at, and each of the diagonals are just mirrors of each other. So for each one of these boxes, we can see the combinations of input settings for each of the 2 factors and see where they are set for the experiment and how they're filling the space for the interior of the experimental region. And what you can see is you see a number of space filling designs to include ours, fills the space quite well. Even some of the maximum entropy or the sphere packing space filling designs typically have holes as well, despite them being traditional space filling designs. The other second order designs only look at the corners and center, and as a result they only are not able to fill the space as well as the space filling designs. And in addition, because of their nature, the way they're constructed, they are not able to construct a third or fourth order or higher regression matrix to capture those higher order effects. Now, in order to quantify the space filling characteristics, we looked at a common measure that's used in experimental design called a modified L2 discrepancy, which is an approximation of this notion of discrepancy, which takes an experimental region and looks at subregions or rectangles within it and compares the volume of that rectangle with the distribution of points in that rectangle to see if it's disproportionate. So for example, in this rectangle 2, there's a disproportionate amount of points in this rectangle compared to its volume. So as a result, there's less of a space filling characteristic. And the point to be made is that we're using a metric that's commonly used in experimental design literature called the ML2 metric. It's evaluated by this expression, and we are trying to minimize this measure. So the lower the ML2 measure, the better space filling characteristic is. Now there's lots of other space filling characteristics out there, but we chose to use this one because it's very common. It's commonly used in a lot of the literature. Now, oftentimes when we have 2 competing objectives, in this case space filling characteristics and second order correlations, we use these Pareto charts to try to find a dominating solution among a set of potential solutions that we can pick from. In this case, on the y-axis, we've got the ML2 metrics that we just described that we're trying to minimize. We've got the row map for the second order regression matrix that we're trying to minimize. So we're trying to drive down to this origin. And you can see, for all practical purposes, our design dominates all others. Now these 2 designs here perform a little bit better than ours in terms of space filling characteristics, but by a very small margin. So that's why I say, for all practical purposes, our designs dominates all the other state-of-the-art designs in terms of both space filling and second order correlations. Okay, now we'll move into our second phase of the so what, and we're going to talk about an empirical experiment we did to see how these designs perform. Now again, we continued with our baseline of 4 factors and 25 design points or rows, and what we wanted to do is look at 2 metrics: the prediction accuracy of how accurate a design captures an output, and also how accurate it's able to estimate the coefficients. Those coefficients are key to understanding those complex behaviors, so that's what we're trying to get at in this study. To do that, we arbitrarily chose 6 different true model response surfaces that represent a wide variety of complex output behavior that we may see in a simulation environment. These output true models consist of a second, third, and fourth order model, and also a second and third and fourth order model with step functions or thresholds. Those interesting localized effects that I was talking about earlier in terms of space filling, where the localized area is vastly different than everywhere else in the response surface. So by including a step function, we're trying to see which of these designs across all 6 of these complicated models performs robustly well across all of them and is as expressible as possible to try to capture accurate results for a wide variety of response surfaces. So to do this, we've created a script in MATLAB where for each of these meta models, these true models, for each design, when capable, we created a second, a third, and a fourth order regression matrix to try to fit an estimated surface for these true model surfaces. We used stepwise linear regression, and in the end, we took an 11 by 4 uniform grid and evaluated each of those points at these true models to come up with a true model surface of what it really is. And then with the stepwise linear regression estimated meta model that we use for the regression fits for all these regression matrices, we came up with an estimated surface. And our point is to see how close our estimated surface is to the true model surface by coming up by examining the average squared distance between these two surfaces. The closer they are, the more accurate the prediction accuracy would be. And that's expressed by this term right here, the true model minus the predicted estimated model that we talked about, and see what that metric would be. In addition, we wanted to estimate the coefficient accuracy as well. Now the coefficient has a host of coefficients depending on what model it is based on the form. And we wanted to look at the true model coefficient as a vector and take the vector of the estimated coefficients and take the Euclidean distance between them. The smaller the distance, the closer our estimates are to the true model, and hence we're able to capture whether the coefficients are accurate or not, at least with this metric. And that's the Euclidean distance metric right there. We perform this regression, stepwise regression of these experiments 10,000 times because there is an inherent stochastic nature by including a vector of normal noise to these true models. And now let's go ahead and talk about the results and what we learned from these experiments. Now, first of all, I have to point out that earlier I said that traditional designs cannot fit third and fourth order matrices. So we had to separate the comparisons between our designs and the traditional second order designs. And then a second look at our designs with the other space filling designs that can all fit the higher order models, the higher order regression matrices. So what I'm showing you here, I'm going to orient you to this chart. And the first thing I'm going to do, the first column expresses the 6 true model response surface that has second, third, and fourth order with and without step functions. And for each of these models, I have here the regression matrix that was used in the stepwise linear regression to fit that estimated model. And you can see here all these are using second order regression matrices because the face-centered composite design and the de-optimal traditional design only can do that. They cannot do third and fourth order regression matrices. So the results are here. The prediction accuracy, I'm highlighting the lowest one, which is our objective in yellow. And we can see that ours performs relatively low for most of these, except when the true model is actually a second order model. Now it turns out that if you can assume that the true model is second order, then you should use the traditional designs. But the problem is you can't always assume it's a second order model. It could be of any order. It could be of any complicated surface. So going into a study a priori assuming that a model surface is going to be second order could potentially be a faulty assumption. So we want to have the flexibility to not only fit second order models, but also third and fourth or whatever order model that we may encounter trying to understand the complex behavior. So our design is able to fit not only the second order model, but also capture those interesting localized effects if they're step functions because it fills the space, and provide some consistent results for these terms. Over here on the right here, the reason why this is a non-available area is because essentially we're only using a second order regression matrix to come up with those coefficient estimates. So when there's a third order coefficient and a fourth order coefficient, it makes no sense to make the Euclidean distance calculation between a model that only includes second order, when in actuality there's third and fourth. That's why there's a non-available there. Okay, now this is the second point of comparisons where we exclude the traditional designs because they can't fit a third and fourth order matrix. Here's the same sort of layout in the chart. You got all 6 of these complicated true model response surfaces, and each one of these show the regression matrix that was used to fit those models. And what we can see certainly is that we've got the lowest grand mean across all 6 models, and they're consistent. So there are times, certainly we don't beat all of them in all cases, but for the most part, when they do other designs perform better than ours, they don't perform so much better by a large margin. So the fact is that we are able to show that our model has the lowest grand mean across all these 6 complicated models, which with consistent results, to indicate that they're very robust. They're robust and flexible across a wide variety of response surfaces, which is what the point of this research is all about, is to try to come up with some unique designs that could handle a wide variety of response surfaces. Now, we talked about the 4-factor 25 design point, but in addition, we've created or cataloged up to 12 factors. I should say, as of last night, we've got another one that's 15 factors, but I haven't included that because we just found it. On the y-axis, we show our design with the other leading designs that we did our comparisons with. This is the x-axis. The y-axis is the row map for the second-order regression matrix. And we can see from the different number of factors, from 3 up to 12, our design has the minimum P row map across all these types for a different number of factors. So the point to be made is that our design, there's no design in the literature that performs as well as ours in terms of both correlation and space-filling characteristics. And we submitted a paper to the Transactions on Modeling of Computer Simulations, and we're hoping to hear back from them soon to publish these results. Now, in addition to the second-order regression matrices, we are also able to create other types of designs with this genetic algorithms. The first type of designs are the first-order nearly orthogonal Latin hypercubes that were already contributed by other researchers in the past. So this isn't an original contribution, but we are able to replicate these types of design as well. The only thing different in this case is that they don't rely on expensive optimization software, and we can utilize free open source Java programming to just execute the algorithm to come up with these designs. A saturated design, it just happens to be a design that has the number of experiments that is one more than the number of columns. And it's the most efficient design possible to get enough degrees of freedom to actually fit the model that you desire. Now, what is an original contribution in this chart are these things called quadratic nearly orthogonal Latin hypercubes, because these are designs that include not only the linear terms, but also the quadratic terms as well, but exclude the two-way interactions. Okay, so we didn't want to stop here. Up to this point, we just talked about continuous factors, and we also don't want to. We also want to remember the fact that simulation studies often have a mix of factor types. Not only do they have continuous factors, but they have discrete and two-way interactions as well, and we want to be able to capture these. So there's been some research in the past by Elcio Vieta that he developed a mixed integer linear program to minimize the first-order correlation among all linear terms for a discrete and categorical factor. It's important to consider these. Again, it makes no sense to have 1.5 aircraft carriers. So in the past, we end up rounding, and it screws up the analysis. So we want to be able to capture discrete elements and categorical qualitative factors within our simulation study. So this was a tremendous advancement by Elcio to be able to create designs that can handle discrete and categorical factors. And what we did is we advanced it even further by creating discrete designs that can handle second-order terms, whereas in the previous algorithms they could not. Now, because the simulation experimenters require a host of factor types, each of these discrete and categorical levels have a number of levels set for every category, whether it's 1, 2, or 3, or 0 to 2, or whatever it may be. What ends up happening is that there's an infinite amount of factor combinations that can result with the different number of types and levels for each of the discrete and categorical factors. So it's of a benefit to the wider community to have a freely available design creator that can capture all these types of factors for the particular simulation experiment that they're going to perform. This is a busy chart, so let me just introduce it to you first before I get into the weeds about it. But because our next part, we're almost done. Our next part is to talk about our application of these designs. We applied them in some study that we did in the systems engineering department, where the Office of Naval Research has sponsored the systems department to try to investigate how they can better build ships with a better design concept. And I'll start out by saying that the concept is that traditionally naval architects were building ships around the platform, and they were taking the combat systems and they were putting the combat systems on the platform and designing the combat systems around the constraints of what the platform was. So in the end, there could be some problems, or there just wasn't feasible ways of getting the combat systems because you're constricted to what the whole is. Now, what the SE department wants to do is to try to reverse the paradigm completely and try to design the platform around the combat systems and not be constrained by what that platform is. So how to do that, the notion is way early in the systems design process. We want to leverage computer simulation models to put these ships in an operational environment to see how it performs, simultaneously taking in consideration the physical characteristics of these designs to try to create an understanding of how we can link the operational effectiveness to the ship physical parameters that are necessary to create the ship and accomplish the mission. So to do that, I've got this busy chart here to first show you on the left side where we have an operational environment that we're concerned with, and we have a whole multitude of simulation models. That could be more than one simulation models, and each one of the simulation models can have multiple outputs. Each one of these outputs would represent a measure of effectiveness that we're concerned about in terms of how well the ship performs in an operational scenario, among different operational scenarios, certainly. We perform a design of experiments on each one of these simulation models across the multitude of outputs that may result. And for each output, we have a meta-model, a polynomial expression that acts as a surrogate to these simulation models that can quantify the input and output relation between the design parameters and the output of interest, which happens to be the measures of effectiveness that's defined by these simulation models. Now we do the same thing over here on the right side with the ship synthesis model, where these ship synthesis models define the feasibility, and they take into consider the design characteristics to ensure it's a feasible ship. And you got a number of synthesis outputs that ensure the ship is stable and it has the ability to actually be put in the water and be used. So by creating designs with this synthesis model and creating meta models of the outputs for the synthesis model as well, with the collection of meta models that we have both on the operational and physical side, we can combine all these meta models into a trace-based environment by leveraging these contour profilers. And in these contour profilers, the colors represent each of the meta models. The meta models, the shape of these colored curvature meta models are defined by the coefficients that are in each one of these parametric models. So the point is that it's very important that we get as accurate meta models as possible, so that when we put these equations into this trace-based environment, that we're actually going to be able to capture the true curvatures that may exist. The curvatures are defined by the number of constraints, or the constraints that you impose on these characteristics that you're concerned with. So the shapes of these colored contours are given by these coefficients, and ensuring that they're as accurate as possible is really the point of using our designs. So in the end, we were able to provide these designs to a number of students that tested this methodologies to get the most accurate meta models as they can possibly do to consider the second order effects as well. Okay, before I get into the contributions, I want to say that certainly my intent here is to talk about an original contribution to knowledge, but also we don't want to just take my dissertation and put it on the shelf, and especially since no one's going to read 150 pages. We want to make these experimental designs widely available to the community. And to do that, we created a front-end user interface for the algorithm that is also free, that can be downloaded with just two files, an Excel file and also an executable jar file. Downloading that from the web, opening this Excel tool up, be able to specify your experimental conditions, some important input parameters for the algorithm, press the button and run execute the algorithm, and have the design that the user needs for their experimental simulations that they need to do. So the thing I want to point out is that this algorithm requires no licensed software, and is freely available, and it doesn't rely on any the expensive software that a lot of the previous algorithms did. Okay. So my contributions. First, I'll point out that I've constructed the first ever second order nearly orthogonal Latin hypercube that never existed before. I've also advanced it further by creating these second order nearly orthogonal balance designs that account for discrete factors. These designs have a lot of significant events that we want to make note of here. First of all, they minimize the correlations for the most common meta model used to analyze complex simulations. Secondly, they fill the space so that they can detect thresholds or step functions or interesting behavior in those localized effect areas so that we can understand what's going on in the interior of the space. They can fit a wide variety of response surfaces with one single experiment, whether it's first, second, or third, or whatever model you want to investigate in. And they happen to outperform the state-of-the-art designs in terms of flexibility across a wide variety of complex models that we may encounter in a simulation study. Now, these designs have directly impacted some research here at the operations or at the Systems Engineering Department that were sponsored by the Office of Naval Research. The System Engineering Department will continue to use these designs in some research involving the Army and Marine Corps for their model-based system engineering concept. And again, by making these designs freely available and be able to download it from the web, we make it widely available to the community. And if we look back in the history of the Operations Seed Center, or the Seeds Department within the Operations Research Department, there's about 100 students that's used these nearly orthogonal Latin hypercubes. And they've downloaded these designs from the website using continuous factors. And despite their limitations, they used them, and they had a lot of success with their thesis and their research. Now, with the invention of these new designs and the ability to have them freely available, these designs become the new first resort for all OR students within the Seed Center to use these designs for their studies. And in addition, these experimental designs are not only going to benefit the students here at MPS, but in the OR department, the MOVES, and the System Engineering Department, but they'll also benefit the Department of Defense and all areas of science that use simulations to analyze complex simulations. So with that, that concludes my presentation. I'll open it up for questions.
Let me first start and see if there's any committee members that have any questions. I'll defer to other folks on the committee.
Yeah, so what are future directions, next steps? How should someone, a follow-on researcher, PhD student, what would the next steps that you would recommend that they would take?
Okay. Yeah. Well, I got them right here. So the first off, what we were able to do in terms of the categorical factors is do what has been done before with LCL Viera. We're able to create these first order categorical factors and include them to augment them, what we have, but we weren't able to capture the categorical interactions that may exist. The categorical interactions, we certainly tried, and we actually performed that in the algorithm, but they became very difficult because in essence, indicator variables within the categorical factor had a bunch of ones and zeros, and when you make an interaction term with a column that has a bunch of ones and zeros, you inherently get a lot of zeros. So interaction columns of categories that have a lot of zeros are inherently correlated with another column that has a lot of zeros, so we had problems minimizing those interactions among categorical variables. But it could be an area of research that we can look into when we start investigating orthogonal designs, and certainly someone can see if they can capture any solutions in terms of how to handle categorical two-way interactions. Secondly, we can certainly create third order nearly orthogonal Latin hypercubes. And also what we haven't done is we can also try to incorporate experimental constraints so that one factor may only be set in a particular setting that may depend on some other factor. So in essence, you end up having holes in the experimental regions because they're not allowed to experiment in those regions. So injecting or incorporating some of these constraints in the algorithm would help define what the proper experimental conditions would be for a user. And lastly, we can use the algorithm to test other fitness functions potentially, rather than just the row map. It could be used for whatever fitness function a user may want to use.
So I guess the 15 column nearly orthogonal Latin hyper second order is done. How many runs did that? How many rows did it take? And how long?
It took 1,000 rows. It took 5.5 days to run. If you didn't do the jiggle parameter, 2 days, and you get 6%, and it ended up being 0.59% with jiggling. So jiggling didn't really have much of an effect. So, in fact, I've still got some time here at MPS, and I still plan to put some more runs on the high-performance computer to try to catalog more designs that are beyond 15, just to have them. That way, we can become consumers of them, and you know what? Maybe we can get up to 20 factors, and there's still maybe a lot of experiments that are required, but we'll have them available to us, and the user can decide whether they want to use it. So there are times when we want to have thousands of experiments. So.
how would you change your algorithm if you had an initial design that was from one of the other groups of designs that you have? So linear orthogonal hybrid group that already has a KNN already set up. How would you incorporate that as part of your overall algorithm to build on, since you're
To add columns?
Yep.
It already does.
So
It already does. In fact, it's in the front end. You've got a parameter that's a Boolean parameter, true or false, whether you're going to start with an existing design. Very simple. And the user interface has it all set up to whether you may start out with the catalog designs that we've created for the continuous factors. You press a button, you include it in the start design, then you can augment it with whatever you want, or you can include some of your designs, and then augment it to whatever factor types of whatever levels that you specify in that area for the input. So it has that capability now.
Just follow on that. And does that save you on the performance of the algorithms that, especially in the number of days and so on that you've seen?
Yeah, absolutely. I mean, certainly in terms of the second order continuous factors, for example, with 12 factor, that takes 3 days. You don't have to wait that long. You can just add to it, augment it with whatever discrete or categorical or additional continuous factors. Now keep in mind though, when you add designs to an existing catalog design that was second order, we did the best we can with those number of design points. So when you augment additional columns to it, you're not going to get correlations minimized for the full second order model. But you can get it for linear terms, and you know what? You can also get it for linear and quadratic terms. What you'll sacrifice though is those interaction terms. So in essence, if you have 10 factors that's catalog and you got a 12 factor experimental condition and you want to add 2 factors to it, those 2 factors at worst would have problems with the two-way interactions among only those 2 factors. But as a result, you get the specified number of experiments for 10 factors and 2 factors that can at least minimize it for main quadratics only. Sir?
Yeah, if you go back to that, the busy chart you had there, the one that really shows the overall process for that. It's a great chart, by the way, because it really does pull all the stuff together about what we're trying to do. But one of the challenges we have in doing chip design is that those models there for chip synthesis are generally not self-converging. They require the naval architect to make a change, and then they have to balance the design by looking at it to get the point where stability is correct and all those things. So it's not like something you can just put in inputs and it'll converge to a feasible solution. So how does your method lead someone to be able to look at the fact that a naval architect would have to do each of those designs and yet still be useful, and because you can't do 1,000 designs. I mean, it's just going to take too long with all the manual intervention. But where's the impact of what you can have to be able to make this useful to that end of the design spectrum, where the model doesn't self-converge?
Well, just so I understand, I mean, if the world was perfect and you could have every possible combination experiment with, then everything would be great. But we can't. We can't look at every possible combination. So we use these efficient designs to try to capture this polynomial function. Now the limitation is that they are polynomial functions. They're continuous functions that we're representing by these meta models that are extrapolating between all those points that we're not capturing in between. Now there are ability to use discrete and categorical variables that shift the intercepts or shift what the response looked like based on the discrete or category. But in the end, the limitation in this is that they are continuous functions that we're trying to slide around in this trade space to see how we can come up with a feasible ship. So in terms of our ability to address the need to look at what's in between, we have to recognize the limitations in using a polynomial function that's in a continuous form.
Yeah. And I said we have been, I'd say for the last 10 years, more focused on, 10 or 15 years on the way you mentioned the Aerospace Design Lab at Georgia Tech had done this in central composite designs, box banking designs, and having to limit the number of factors so we can at least create the meta model. But it seems that we're losing out on coverage of the design space because, as you said, you can see where you're not populating design space, number one. And that reducing the number of factors, there are a number of factors we'd like to include. So just wondering if I think you may have had a chart that might address this around slides 26 or 27. I think you had something, how many designs you could, this was design points in order to get for a particular number of factors, how many design points you'd have to get to cover the space?
Yes. Yeah.
So is this, so if we wanted to use some of these methods, you could sort of find something that would be a balance in how many designs somebody thinks they could make,
Yep.
and yet include that many factors, because again, if you tried to use a central compositor box banking with 30 factors, you
Right.
would off the charts.
Right. Well, in terms of the number of experiments required for a particular fit of a metamodel, it goes into which metamodel you want to fit first. So if it's a second order, let's go with a 4-factor. We have 4 factors. Then it's going to require the quadratics and two-way interactions, which equate to 14 terms that we're going to fit. If it happens to be a third-order model, we have to include 22 terms. And a fourth-order model, we need 27 terms. Now, we decide which model we want to fit, but based on that, we have to have at least one row, or one experiment for each degree of freedom for each of those terms that we're going to try to capture. So if we don't care about third-order terms, then we don't need that many experiments. We only need, in terms of a saturated design for a second-order model, we need at least 15 experiments. So as you go through and decide how many factors you are, you not only want to consider how many factors of interest you have, but you want to consider how many higher-order terms you want to include to analyze. And if it is a higher order, you're going to require additional degrees of freedom to be able to fit all these terms in this n-dimensional space to create this surface with enough degrees of freedom to capture those additional high-order terms. But if you limit it just to the linear terms, then you can have a lot less experiments.
Right. And we usually figure we need some of that to capture some of those nonlinear terms. We just
Right.
don't know what order is necessary. I think. So I'm just trying to figure out the balance between, we may have to develop more computational tools that are more effective at sort of self-converging, so we can do more designs to be able to populate that space rather than so much manual intervention in the designer's mind and putting that into actually manipulating the tool.
Right.
Because the desire is to actually get to more design space exploration with better coverage and
Yep.
to capture some of the nonlinear effects that I think we're losing with the second order curve fits and
Yep.
the gaps. So
Mm-hmm.
it seems like this may lead to some point to a direction that we may need to go in for our own computational tools to synthesize the designs. And
Yep.
the effort there would pay off if you've got something here that can show better coverage.
Absolutely, I think so. And there are limitations in that, when we want to include all the second-order terms, we're only talking 12 factors. In reality, there could be hundreds of factors. So we can do this as a sequential approach as well. By taking a nearly orthogonal Latin hypercube that only looks at the linear terms only, we can handle hundreds of factors easily. I mean, we can create it. I got one here that's 100 factors with 200 design points. I mean, we can create one with 101 design points if needed, because it's got one additional experiment for that degree of freedom that's needed. But lost my point. But what I'm saying is okay. So the sequential approach. So we get 100 factors and we narrow it down the ones that are significant. We can perform additional experiments on the factors that are significant to confirm or deny whether those high-order interactions or effects actually exist to get a more refined or accurate metamodel. So doing a sequential approach when you have a lot of factors is certainly something that should be within the methodology as well to try to get at the best.
That's the approach that naval architects would take in doing a design anyway. So.
It's the same what we did before, but now we can do more factors and we can capture more complicated behavior more accurately.
Which is what we're doing.
Yeah.
With the least amount of effort.
Yep.
Okay, a couple of things. Kind of going back to the threshold effects. I mean, you created that by fiat. Have you encountered any particular simulation models that exhibit this threshold effect?
Personally, I haven't, but I can point to some research that that Professor Lucas and Tom Chapa have looked to look at some. When they were looking at a particular model, they were trying to find, doing some V&V on the thing, and they wanted to see what conditions happen for particular circumstances. And I think they found a situation where there was a threshold where if the data was grouped in one area, it was completely different than everywhere else. And being able to identify that change point was certainly of a concern. I could tell you a practical example that Paul Sanchez has always taught me And certainly with this example, you can probably see this happen in many simulations. But if we're investigating the performance of a cargo parachute, and we're interested in the rate of descent as the parachute descends based on the amount of weight it's under, the more weight, the more the rate of descent increases, up to a point where it collapses. And then that rate of descent steps up tremendously to a point where it just smashes to the ground. And understanding where that occurs is very important in terms of our ability to understand the characteristics of that parachute. So finding having a design that explores the space, not only to look at the corners or center, but finding out where that change point or that threshold may occur is something that can be of interest for us, not only in physical experiments, but also simulations as well. Now, oftentimes I could say that there are a lot of fitting techniques that use neural nets and all these complicated black spot techniques to really handle, or Gaussian processes that fit it exactly. But ultimately, we're trying to understand behavior. We're trying to understand behavior by just using basic ordinary least squares to see how those coefficients impact the response. And if there happens to be a threshold, we can use non-parametric methods like partition trees that groups data into two separate groups so that the mean between the groups are as far apart as possible, to try to see if we can explain as much of the variation as possible by a particular split. So if it happens to be a situation where we do a partition split and we have these two groups and it happens to explain a lot of variation, then we could potentially create an indicator variable that would account for this change point where it groups the data into two separate places, and that could explain more of the variation to help understand the behavior.
Okay, I'm curious, when you used a design to study the design, how did you generate the design for that?
Yeah. Well, we looked at the number of factors of interest, and I just ran the algorithm for the number of factors I needed, for the number of rows, to get me the highest order model as possible. And it was just a matter of setting the number of columns and number of rows I wanted, and creating the design that would meet that.
In the parameters that you were looking to find,
right.
What the good ones were, you had to set those in order to generate the design to study that. So
right. So I just pulled them out. I just used the ones that seemed to work. In fact, we did create nearly orthogonal Latin hypercubes with just parameters that came out of the air. And then it wasn't until we did the International Data Farming Workshop here last year that we spent a week on performing these experimental designs to investigate the parameters. So certainly the fact that we didn't have the optimal appropriate settings for the parameters to create the designs were nearly orthogonal. So it didn't really matter. We had the designs that had minimized the row map. But again, we still want to understand if there's any way to improve the search, maybe the length of time, or for whatever maybe more efficient. And that's what was the significance of doing the experimental designs of the appropriate settings. In the end, it was extremely stochastic to begin with, but it's certainly better than just blindly coming up with something out of the air.
Did you look into maybe in your experiments? Did you try overfitting models? Like, in other words, if you had a second order model to fit, how the different designs performed when you fit, say, a third order model or a fourth order model to them?
Here is an example of where a second order model fits a higher order model. So this is actually underfitting. So overfitting.
So take a second order model, fit say a third order model to it, and see how the different ones.
Yes, like here. A second order model that fit a higher order model, and there's probably a case.
I'm looking the other way. Take a third order model, take a second order model, and fit a third order model to it using because then you don't know. I mean, if the underlying is in fact more of a second order model, but you think it's third, and you overfit, then that could be kind of. It seems to me that a design may perform better or worse under those circumstances. In other words, identifying whether or not it's second order when you're fitting these larger terms.
Looking at this, we didn't overfit. I mean, you can see we underfit in a lot of cases, but we didn't never overfit to see what the performance was. But at least analytically, I think when we overfit, that the impacts on the correlations are certainly not nearly impactful if we underfit and we have higher correlation. So in other words, if there's high correlations and we overfit, it's not nearly as extreme as if we underfit and have correlations. Because you have more degrees of freedom to capture what you're trying to fit there.
Okay, well, I'll open it up to the audience. I know, Dan, you have a question?
Thank you. Nicely presented and important topic. If you go to 29, I have a comment. This is the chart that Cliff likes and I do too, and I'm particularly pleased that cost in the bottom right four-letter word is the only bolded output. If you go to 23, I missed a point here. You have 6 models that you are using as test cases.
Mm-hmm.
I missed the pedigree of those 6 models. Where did they come from?
Well, certainly the pedigree in terms of the second, third, and fourth order models, just those, we wanted to include a wide variety of models that had those additional terms. Now, in terms of the pedigree, why is it 10 versus 6 and all that business?
Is it just exemplar? Just a sample? Or just
It's not randomly a sample, because certainly we want to have an example of where potentially designs that have problems with correlation could impact us. Because in these results, there's certainly situations where our designs do not win, as you see the yellow areas. And there's no perfect design, it never is. And we are leaning on the fact that we are nearly guaranteeing that all factors won't be confounded just based on the characteristics of the row map and the space filling characteristics. But in reality, because no design is perfect, there is other designs that may perform well or better than ours for that particular model. So we selected true models that there was problems with the other designs to demonstrate that, yes, we either can get lucky and have problems with correlations, and if there happens to be a term that's correlated and it's in the true model, then we're unlucky. But if we get lucky, if there's a term that's in the model that's not correlated with, then it's not a problem. Our designs minimize that problem from all combinations. But the designs that have correlation problems, they only occur with particular pairs. And if those pairs aren't in these models, then they're going to perform just as well. So I did find true models where there was problems with some of the designs in terms of correlation. So for example, X3 may have been correlated highly with this interaction term on one design. So I didn't arbitrarily pick them. The pedigree was to try to find designs that showed an example where when there is correlations, this is the impact.
the first one, 10 plus 10x2, etc. It's not a randomly chosen model?
No, it's not.
It has parents and a pedigree and a cachet. It came from some prior work.
No. This is something that I arbitrarily chosen.
It came from some work you did in order to have a particular structure, or it's just a sort of a randomly chosen set of coefficients?
It's a set of coefficients that highlights the problem areas that other designs have because they have high correlation. Because if we didn't do that, then designs perform well if they get lucky and not have problems with correlation.
Thank you.
I was going to ask the same question, but you beat me to it. But have you considered randomizing the coefficients so that your following tables then would be representative of what you might see, as opposed to possibly being representative of a cherry-picked case?
Mm-hmm. No, we haven't done that.
Okay.
I mean, we certainly.
The other question I had, you have your Pareto slide,
Mm-hmm.
which is a lovely slide.
Yes, indeed.
That's a wonderful thing. Have you considered taking that to a three-dimensional Pareto surface where you're taking into account number of design points and stuff?
And factors. You would have to, right? No, I see. Yeah, you can fixate the number of columns and also do that third dimension just to see what's required. Because that's great, because the box Ben it's cataloged. It is what it is. So when you go to the next higher one, you get whatever that is. Whereas ours are a lot more efficient. That'd be a neat chart.
Okay. And then my third question was related to the earlier questioning. Basically, you know, it looked to me like you had back on 23, some of your models did have indicator plateaus, and I was wondering whether that, whether you would hit these models up with partition trees
I did.
and hybrid formulations as opposed to going with straight polynomials.
No, I didn't mention that, just in the interest of time, but to answer your question, we were doing this algorithm with an algorithm with the MATLAB script, and we're assuming that when there is a step function, because we're injecting it, we're putting it in there, that there will be a partition. And in fact, there is. So we put within the algorithm one partition split, and we created an indicator variable that had a 1 for the area where it was above that and a 0 for the area that was below that. And in essence, we've included an additional column in the regression matrix that captured that indicator variable for all step functions to enable us to understand that behavior. So in the times when there were second order designs that only look at the corners that can't fit those higher order matrices and they don't fill the space, they just didn't, when they made that split, they didn't find it. They didn't find that indicator, and as a result, their estimates weren't as accurate as the space filling designs.
So I was wondering, as a corollary of that, could that approach be helpful with the ship design problem in terms of putting in indicators for when the factors take you infeasible and aiding your designers in what regions to avoid?
Yeah, that's right.
Yeah, I think that's a great idea.
Possible, yeah.
But those infeasibilities are really cross variables. You can have a long ship, but not a narrow beam.
But you can have additional partitions, layers of partitions.
Indicator or partition interactions.
Yes.
That would definitely capture.
Mm-hmm. So, I mean, they're hard to interpret when you start creating these partitions into multiple splits. So you group the data into two groups, and then you group each of those two groups into multiple groups. And there's a story behind all those. And that story could be these combinations of interactions to find feasibility that are oftentimes hard to explain. I mean, one of the benefits of using ordinary least squares is that we can explain the impact by these coefficients. But now that we have a coefficient that has an indicator variable with multiple partition, it just makes it very difficult to interpret to the operational commander or to any user. But I think it has potential to see how that would be able to define the infeasibility or the area. So it's really a matter of the SE students knowing partition trees and taking 4333.
We have a course on that.
Any others? Well, I have one final comment. I promise there's a question at the end. And I just wanted to ask you about sort of go back, you know, we've been working on this, the application of this over the last couple of years on this project, and you've been working with us with Office of Naval Research as our sponsor. We've been to a number of workshops with our sponsor and some of the colleagues that we've worked with at Virginia Tech and Georgia Tech, and then our Italian friends, both from the shipbuilding folks and then an Italian firm that also does modeling and simulation analysis, and also folks from the University of Genoa. And then we've done presentations, briefings at Moore's Conference, we did our review at Carter Rock with, and so we had quite an audience there from folks who are shipbuilders, do that for a living. And then we had also groups from Department of Defense that came out. I guess there's a question, and it's more of from your perspective, and you've had the opportunity to present this and get feedback and have discussions with some of these folks that are out there. As you mentioned, we're very interested in getting this out and getting users and getting communities interested in applying this. What are some of the maybe the memorable feedback or some of the things that they've said to you or you discussed about or maybe more of a generic sort of thing to say, is it been favorable? Have you gotten good responses from some potential colleagues and others who see this work. I forgot to mention the Naval Modeling and Simulation Office, the acquisition folks who saw this as well. So just see what your thoughts were.
Maybe on both spectrums, I think. On one end, I think the Italians, they don't believe it. They don't believe that you can possibly look at hundreds of factors and get all the insights that you can get out of these nearly orthogonal line hybrid cubes. And
they're set in their ways. They've got their design models, and they have a turnaround time to ONR Global in this program. And so once we introduced these other designs, like, wait a minute, we have to go back to the beginning and start our analysis all over again. And I think that was the least part of it.
Right.
Well, the Naval Sea Systems Command, naval architects didn't believe the box banking and central composite design implementations, 10 years ago either. So they were still kind of didn't understand what could you possibly do with a model that you can move in real time. They said that you can't be designing a ship with that. So.
So does that mean in 2020 they'll believe these?
I hope we can get that latency down a little bit shorter.
Well, I think there are some positive feedback I got over the times we went around. Certainly the people who appreciate experimental designs and can understand the importance of having efficient designs and looking at more factors. The people at Georgia Tech really recognize, and they've been chomping at the bit, asking when is there going to be a custom design created that we can just use it ourselves. And now that we have that available, we're excited to be able to keep that open and offer that to everybody, so they can be consumers of those designs, and maybe the SE department can continue their relationship with Georgia Tech with that realm. So, it really goes into who's involved and understands experimental designs. That really determines the feedback I've gotten. So positive and negative overall, I think.
All right.
Just one last thing about you were talking about sort of licensed software. Does the spreadsheet run on require Excel?
Yes.
If so, that requires a license. You might want to be careful.
Yes, I stand corrected.
Well, thank you very much, Alex. Very well.